All right, hi everyone. So the objectives of this lecture is to show you basically show and use and analyze the Navier-Stokes equations to find velocity profiles, etc. You can do forces too. So what we want to do is I'm not going to show you the complete derivation, just show you the brief concepts and then get right to practice problems. So if you remember, the sum of the forces in momentum, linear momentum for control volume, where sum of the forces equals the change in momentum per unit time of the control volume plus the momentum out minus momentum in. So just like the previous lecture in conservation of mass in differential form, we can do the same thing for momentum and only look at a differential element inside the flow. So again, we have momentum coming in and momentum going out. The derivation is a lot more complicated, so I'm going to just kind of briefly review like some of the forces. We have weight, we have pressure and viscous, shear forces. The change of mv over dt is your momentum change inside the box, and then these are the momentums in or out of the box on the surfaces. Okay, so when you can do the differential analysis, the book has it, you end up getting equations, momentum equations, all right? And the incompressible form of these is what we call the Navier-Stokes equations. There's going to be three sets of equations, x, y, and z. So here is the x direction, all right? The terms on the left are your momentum in and out, and the terms on the right are your forces. So here you have pressure. Here you have gravity, here you have viscous forces, okay? And this is just your momentum change in and out. So if I go show you, I will have this sheet posted. This sheet has the equations that you're going to be using, I'm going to use, and there's a practice problem that you're going to use. You can just print these out and solve it. So here is your continuity equation that I showed you before, okay? Conservation of mass. These three equations are basically momentum in the x, y, and z. All right, so here is du dt, du dx, dvu dy. Okay, and this is so basically in differential form of your linear momentum. And these are basically incompressible Navier-Stokes equations. So these are the Navier-Stokes equations. And we're going to use these sets of equations to solve for velocity profile. So that's an example that I'm going to show you right now. All right, so again, we're going to use these equations, and so here's an example just to make sure you get a feel of what's going on here. So consider a two-dimensional incompressible plane viscous flow between two parallel plates, a distance 2h apart. We assume that the plates are very wide and very long, so the flow is essentially axial, so u is not equal to 0, but v and w are 0. The present case has the upper plate moving at constant v, but there's no pressure gradient. Neglect gravity effects and find the velocity profile. All right, so what we do is we're going to start with the continuity equation. All right, so let's start right with this. du dx, we don't know, we're not sure how that works, okay? dv dy, what do we say for the velocity in the y direction? That was 0. How about from this statement, the w direction? That's 0. So from that equation, du dx equals 0. What does that mean? That means u doesn't change or function along x. Okay, this is a two-direction. This is really just 2D, so it's 2D. So that means u is a function, of y. So that means that this right here, and this point here, this velocity profile along the y direction up is going to be the same no matter where you are along the x direction. But if you notice, the velocity here is 0 and the velocity up here is v. So we know that u changes in the y direction. All right, so that's the continuity equation. Now let's look at the Navier-Stokes equations. We do not have to worry about the w direction because it's only two directions. Okay, so let's do this. We're going to assume that it's steady state. So that term goes away. Let's do the x direction first. Okay, and what did we say about du dx is 0? So that term's gone. How about this term? Well, look, what did we say for v? Is there v? Nope. So that whole term is gone. Is there w? Nope. And it said that the pressure gradient, if we go back up here, right there is no pressure gradient. So that term goes away. And we're going to neglect gravity. Yep, right there. Neglect gravity. And we know that this term is 0. We don't know anything about that term, and we know there's no z direction. All right, so based on this equation, everything here is 0 on the left. This is all 0. That's 0, 0, 0. We end up getting mu d squared dy squared equals 0, or really just d squared u. Sorry. I'll write it right here. D squared u dy squared equals 0 because the mu goes away. Alright, so let's just double check the y direction. We said there's no pressure gradient, there's no gravity. We said that there's no v, or w. So those two terms can go away. And there's no v, so that goes away. Oh, there's no v, and so all that's 0. So from the continuity in the Navier-Stokes equations, we end up getting that du dx is 0 from the continuity, and that again means that the velocity profile at this x position and this x position are the same exact position. They're the same for x. However, because it's 2D, that means that the velocity profile is only changing in the y direction. So if we go to our Navier-Stokes equations, x and y, because we're only looking at 2D, when we look at each variable, we cancel. All right, and we end up getting this. So d squared u over dy squared is 0. So now what we're going to do now is we're going to solve that differential equation. I'm going to do that down here. Now, this is partials. We don't have to do partials anymore because it's only one variable, which is y, and that's 0. All right, so what we do is we can call that u double prime, and we're going to integrate it. When we integrate it, we get u prime. When we integrate to 0, we get a constant. All right. Now we're going to integrate again. We get u equals c1 times y plus another constant. All right. This is our equation for u. Look, it's only a function of y. All right, so I'm going to write this stuff over here. Now, how do we actually get the constants? Well, we have to apply the boundary conditions. BCs. The first boundary condition, we need two boundary conditions because it's second order. Y equals plus h, u equals big V. Second case, and it's minus h, u is equal to 0. All right, so we pick both of these and we plug in. Let's do the easy one. Let's do boundary condition number 1. So V equals C1 times H plus C2. All right, and we'll do boundary condition number 2. 0 equals C1 times negative H plus C2. What do we get? We have 2 equations, 2 unknowns. And we solve for them, and we end up getting, finally, U equals V over 2H times Y plus V over 2, which we can bring over this Y over 2H plus 1/2. Okay, so that is the velocity profile in the Y direction. And it's going in the X direction. That's why it's U. Again, 0 here and V here. So that's one example of using the continuity and Navier-Stokes equations. All right, so now we know the details of the velocity profile anywhere along the Y direction. All right, so here's another example. All right, so both plates are fixed and the pressure varies in the X directions. Find the velocity profile. All right. Okay, we're going to assume steady state. It's 2D and it's fully developed. All right, so 2D, get rid of this direction. All right, so let's start with the continuity equation again. Based on this, what direction does the velocity look like it's going in? It's only going in the X direction. Okay. We know there's none of this. And there's no V. So from this, we get du dx equals 0, and therefore u is a function of y. Again, this spot at x1 and this spot at x2 will have the same velocity profile along the y direction. All right, boom. From the continuity, we get this. So let's plug in, so it's steady state, so that term goes away. We just said that du dx is 0, so that term's gone away. There's no v and no w. There is a pressure gradient. We're going to ignore gravity. We can put that in there too. Okay, and this is 0. We don't know about this, and we do know about that. Okay, so based on this, we get negative dp dx equals, plus mu d squared u dy squared equals 0. Okay, and because there's no velocity in the v, all these terms go away. Oops. Sorry, not that one. Because there is a pressure gradient, so we end up getting dp dy equals 0. So based on this, what does that mean? That p is a function of x. So the pressure does not vary along the y direction, only the x direction. So let's recap. Continuity equation. We know that there's no velocity in the y direction, so that term's garbage, and we know it's only 2D, so that's garbage. So du dx is 0, indicating that u doesn't change in the x direction. At this x position and this x position, we're going to have the same velocity profile along the y direction. So u is a function of y. When we look at the y component of the Navier-Stokes equations, the only term left is this equation. dp dy equals 0. that means that the pressure doesn't change in the y direction. It only changes in the x direction. So this pressure here, P1, is greater than P2. All right, so based on the x component of the Navier-Stokes right here, we're going to solve that differential equation and solve for u. All right, so we end up getting, I'm going to do this, mu, and because there's only one variable, which is, oops, p is a function of x. Oh, sorry. Yep. We'll continue. dp dx. Sorry. All right. So, but why do we need partials? We don't, because if we go back to the y component, p is a function of x. Basically, that's assuming, this is now assuming that p is constant. All right. So, or dp dx is constant. So we can change these. So this is really just a constant number. So what I'm going to do is I'm going to solve for this in terms of this. So 1 over mu dp dx. Okay, and then I'm going to integrate this. All this stuff on the left is just a constant, so you get u prime equals dp dx 1 over mu plus a constant. Oops, I forgot to include y. All right, so because we're taking the integral with respect to y, then we're going to integrate again. So we get u equals, I'll put that in there, integrate again, 1 over mu dp dx y squared over 2 plus c1y plus c2. So now we have to apply boundary conditions. So the first one is u equals 0 at y equals plus or minus h. We'll do plus h. And the second one is u equals 0 at equals negative h. And when you do that, you end up getting, apply your boundary conditions, this equation. H squared over 2 mu 1 minus y squared over h squared. Okay, so just to recap what we did here. We had both plates were fixed and the pressure varies in the x direction. All right, so that that basically means that dp dx is a constant. C1, C2, x, doesn't matter, okay? So we use the continuity equations and the Navier-Stokes equations to solve for the velocity profile between those two plates. All right. And what you do is you look at each term and see what you have and cancel what you don't. So please try these out And when I come back, I will help you. There's a practice problem that you can use. All right.